So welcome to to today's plenary talk. It's my great pleasure to welcome Rachel Pries, who's our invited speaker for this lecture. Rachel is a professor at Colorado State University. She got her PhD at UPenn under David Harbitter, and she spent some time as a Vigor postdoc in Columbia before joining the faculty at Colorado State. In addition to her research, she's quite active in outreach and service. She's in particular a founding member of the Women in Numbers Research Network, where we had a little panel or a little meet and greet just a couple of days ago. She was in particular elected a fellow of the American Math Society in 2018, a couple of years ago, for, and I'm quoting this, contributions to arithmetic geometry and service to the math community. Rachel is in particular the founder and co-host of the Vantage seminar. I've posted some information about that in the Zulip channel. This is a virtual seminar that she co-runs with Drew Sutherland, devoted to kind of new trends and open problems in arithmetic geometry and number theory. It's a wonderful virtual seminar, and I should mention that this was started long before COVID. Rachel is an expert in arithmetic geometry, specifically moduli spaces of curves and abelian varieties. And today she'll talk to us about principal polarizations and Shimura data for families of cyclic covers of the projective line. So Rachel, the virtual floor is yours.
Oh, thank you, Renata. And it's wonderful to be introduced by somebody who I know so well. Renata and I started working together intensively on the WIN network in 2007. So yeah, today I'm talking about principal polarizations and Shimura data for families of cyclic covers of the projective line. But before I get started, I'd just like to say a really heartfelt thank you to the organizers. First of all, because organizing such a big conference virtually of this type sounds like an incredible amount of work. And secondly, because the opportunity to connect with other people and to develop new mathematics and learn new mathematics is really especially valuable in this difficult time. So this project is work in progress, which is joint with Wanlin Li, Elena Montavan, and Yanqing Tang. So we all know about the synergy between curves and abelian varieties, but I think this very simple fact needs to be recognized, that if you want to study elliptic curves or curves of genus 2 or 3, then one thing that's very useful is that almost every principally polarized abelian variety of dimension G is the Jacobian of a smooth curve of genus G for G equals 1, 2, and 3. And because there is so much more information about abelian varieties than for curves, in particular a lot of results about deformation theory and also Hecke correspondences, this can often be used to leverage facts about abelian varieties to facts about curves. And for many years, I've used this one fact to prove things about curves, and even curves of arbitrarily high genus. In fact, I was looking through my papers and realized that 10 of the papers I've written just would not have been possible without this fact. And so this project can be viewed as an opportunity for the theory of curves to give back to the theory of abelian varieties, because this is one situation in which it is easier to study the curves than the abelian varieties. And so that's one way to frame this project. So as a bird's eye view, what I'll be talking about today is curves that are cyclic covers of the projective line. And I want to thank Drew for talking about this in the previous talk. So the invariants of these curves are the degree, m, the number of branch points, capital N, the genus, G, and there are Hurwitz spaces which parameterize families of curves with the same invariants. Now the Jacobians of these curves are principally polarized abelian varieties, and they have invariants also. So the dimension, G, the endomorphisms, the signature, and Shimura varieties parameterize families of abelian varieties with the same invariants. And so what our main result is about is that under a condition on the class number of the cyclotomic field Q zeta M for an arbitrary capital N, we determined the Hermitian form and integral Shimura datum of the component of the Shimura variety, which contains the image of the Hurwitz space under the Torelli morphism. And the general strategy is that we're going to identify a distinguished point in this family, a distinguished point whose Jacobian has complex multiplication. And under these constraints coming from algebraic number theory, we can explicitly compute the Shimura datum for that Jacobian. And then we want to write down the Hermitian form coming from the polarization of that Jacobian as a Jacobian. Oh, I should mention, if you have any questions, you should feel free to stop me at any time. So some of the key ingredients are the boundaries of Hurwitz spaces, the narrow class numbers of cyclotomic fields, and an algorithm. I want to emphasize that word since this is an algorithmic number theory conference, an algorithm of Van Bommelen about principal polarizations for abelian varieties with complex multiplication. And so we'll start by talking about the moduli spaces of cyclic covers of the projective line. I realized I put way too much information about algebraic number theory in the slides, so I won't say everything that's on those slides in the algebraic number theory section. And then after the main result, we'll talk about some examples and some discussion of simple types and future directions. So as we saw in Drew's talk, cyclic covers of the projective line of degree m with n branch points. Let's for a moment say they're not ramified at infinity. Then we can describe these with an affine equation. X being given by y to the m is a product as I goes from 1 to capital N of x minus bi to the ai. So for people who are very familiar with the hyperelliptic case when m is 2, it's a little disconcerting that these ai, these numbers ai, can be bigger than 1, because that means that this affine equation looks singular when x equals bi. And that is just really no big deal, because there's a unique smooth projective curve which has this affine equation away from the points bi. So we can just describe this, this curve with an equation of this form. And these numbers, a1 through a capital N, are called the inertia type. Usually we take them to be values between 1 and m minus 1. And they represent how they're sometimes called the canonical generator of inertia at a ramification point. And the sum of them has to be 0 mod m. And for the curve to be connected, the GCD of all of them with m is 1. So these numbers, they determine a lot of information. In particular, they determine the genus of x, because we can use the Riemann-Hurwitz formula to compute the genus of x. And so we'll say gamma, which is the degree, m, the number of branch points, capital N, and this tuple of inertia type is the monodromy data. And it's the arithmetic information that we need to keep track of our Hurwitz space. Now you can always rearrange the order of the branch points. That will rearrange the AIs. You can also change the choice of the root of unity or the generator of the Galois group, and that changes all of the A's consistently by multiplication by some element of Z mod M star. But beyond those equivalences, this monodromy data nails down our Hurwitz space. Now, if we take one of these curves and look at its Jacobian, it's a principally polarized abelian variety of dimension G, and it has an action of Z mu M. What this means is that we can take any vector space associated with the curve. So for example, we could take the vector space of holomorphic one forms on the curve, and we can decompose that into eigenspaces. So this eigenspace Li is the eigenspace of all holomorphic one forms, having the property that the action of zeta m, which comes from the the automorphism of order m on the curve acts by multiplication by zeta to the I. There's no trivial eigenspace because this is a cover of the projective line. And so we can keep track of the dimensions of these eigenspaces. Let's call them f1 through fm minus 1. And the sum of all of them is the genus, which is the dimension of h0 x omega 1. And so this is called the signature type. And in a paper of Connie, you can find a very clean formula to compute each dimension fi in terms of the inertia type A. Fi is minus 1 plus the sum as j goes from 1 to capital N of the fractional part of minus I aj over m. So what the fractional part is you just write down this rational number, and then you take the difference between the floor and this number. And so the data of A determines the data of F, and conversely, the data of the signature type determines the data of A. So this is equivalent information. So for example, let's say we take degree m being 5 and n being 4 branch points, and we choose the inertia type 1, 2, 3, 4. Then the genus turns out to be 4. Here's one way of writing down a curve of this type. But then we can move some of the branch points, b1 to 0, b2 to 1, and b4 to infinity, and rewrite t as b3. We get an easier equation for this curve. The signature turns out to be 1, 1, 1, 1. And it turns out that in the moduli space of curves of genus 4, this family of curves has dimension 1. But if we just look at abelian varieties with an action of z, zeta 5 with signature f, that family has dimension 2 in A4. So more generally, for any monodromy datum gamma, we can take the Hurwitz space, Z sub gamma, which is the moduli space of mu m covers with type gamma. And that space is irreducible, and there's a map to mg. But that data gamma also determines a PEL type Shimura variety, whose points represent principally polarized abelian varieties with an action of Z mu m of signature F. That space can have many components. So let's let S gamma be the component of the Shimura variety, which contains the image of this Hurwitz space Z gamma under the Torelli morphism. And the goal of this project and this talk is to determine the integral Shimura datum for S gamma. All right, so let's just figure out what that means. I think you can tell if you're a Shimura variety person or not based on how you think about elliptic curves. If you like to think about elliptic curves as C modulo a varying lattice, I don't think you're a Shimura variety person. To be a Shimura variety person, you need to think about a fixed lattice, and then as introduced by Delene, understand the complex structure on the tensor product of that lattice with R. And so from that perspective, if you want to find the Shimura datum for the moduli space of abelian varieties, that's given by this data. We need the vector space, q to the 2g. We need the lattice, z to the 2g. And we need a symplectic form from v cross v to q integral on the lattice. And from that, we get a group of symplectic sublimitudes over q, and we get homomorphisms that define Hodge structures. Now we're actually adding an action by q mu m, and so that changes the group to be a smaller group. And the data of the signature is equivalent to the data of an orbit of these homomorphisms under the group. And so when we talk about the integral Shimura datum for S gamma, the way that we're going to express that information is by understanding a vector space. It's a vector space over F, which is Q zeta M, the cyclotomic field. We want to find an OF lattice inside that vector space. And we want to explicitly find a Hermitian form on that vector space, taking integral values on the lattice. So just a quick digression on the dimension. So this Hurwitz family, its dimension grows linearly with G. It's the number of branch points minus 3. But the dimension of the Shimura variety grows quadratically with G. And so usually the dimension of the Shimura variety is much bigger than the dimension of the Hurwitz space. And we say that the monodromy type is special if they have the same dimension. So Monin proved that up to equivalence, there are exactly 20 gammas which are special. And if it's special, what this means is that the Torelli locus is open and dense inside of S gamma, and its points represent Jacobians of smooth curves. But one thing that's cool about our method is it doesn't depend on whether gamma is special or not. So even when the Torelli image of Z gamma has very high codimension and S gamma, we can still use this Torelli image to determine the Shimura variety, the Shimura data for S gamma. So
Rachel, there's a question in the Zulip chat. Björn, are you here? Do you want to ask your question?
Oh yeah, sorry, I didn't want to interrupt your talk. I was just wondering if M is not prime, when you look at the Jacobian of y to the m equals polynomial in x, do you really have the action of the cyclotomic ring Z zeta m, or is it only?
No, you're gonna, well, so for this talk, I'm gonna mostly stick with the case M prime because it's much simpler. One of the simplifications is that we can just work with a cyclotomic field rather than with the algebra Q mu M. And there are going to be other places where it's simpler along the talk too. And so it might be that what I said on the previous slide needs to be made a little more precise for M not prime.
Okay, thank you.
Yeah, are there any other questions?
There was just a statement by Maurice who asserts that smoothness is overrated. I think that's when you were saying that it doesn't matter if it's not a smooth model.
I think it depends. Yeah, for the smooth model, I agree. As an editor, I've seen so many referee reports that have said this whole paper is wrong because this equation is not smooth, and so. All right, so let's see. So the example we talked about before, gamma being 5, 4, 1, 2, 3, 4, that's not special, as we saw. But Monin enumerated his examples. And so, for instance, his 11th example is gamma being 5, 4, 1, 3, 3, 3, and that has signature 1, 2, 0, 1, and that is special. Okay, so here we start a lullaby on algebraic number theory. Let's just remember some things about complex multiplication. So we're going to take a CM field of degree 2n over q, such as the cyclotomic field, and we'll take its maximal totally real subfield L naught, which has degree n over q. And a CM type of L is an ordered set of distinct embeddings from L into C, no two of which are complex conjugate. And we'll say that that CM type is simple if it's not induced from the CM type of a proper CM subfield of L. So if we have a complex torus A, so that the endomorphism algebra contains L, we can say that A will have type L phi if the complex representation of the endomorphism algebra on the tangent space of A is isomorphic to the sum of the phi and phi. And that implies in particular that the dimension of A is as n. So if in addition the endomorphism ring is OL, we'll say that A has type OL phi. And so this is the example that everything depends on. If we take M to be prime and L to be the cyclotomic field Q zeta M, And we take the embedding, which takes our choice of mth root of unity to e to the 2 pi I over m to the j. Then we can look at the Jacobian of a 3 branch point cover. So if we have a cover with 3 branch points, then this Jacobian has type OL phi. And the way we figure out what phi is by looking at the signature and seeing which entries of the signature are positive. And that tells us exactly which embeddings should be in capital phi. So for example, let's say m is 5 and capital N is 3 and a is 1, 2, 2. So here's an affine equation which has this, this inertia type, and the signature is 1, 0, 1, 0. So we would take capital phi to be sigma 1, sigma 3. And already you can see, if you're interested in the case of m not being prime, this is already not quite true that the Jacobian automatically has Cm. You need constraints on the inertia type for that to be true. So we don't need everything on this slide, but here's one important thing that you can find in Lang's book, is that if you have a simple type, L phi, then the class group of L is in bijection with the set of isomorphism classes of complex tori of type OL phi. And so this condition of being simple is crucial for this. And so we can see the importance of the simple condition already in this algebraic number theory. Oh, I forgot to say one thing I wanted to say about this previous slide, which is that much of what's happening in the next 15 minutes of the talk is going to be about whether we can find the Shimura datum for this 3 branch point cover. And we'd like to be able to nail that Shimura datum down exactly. So we need to find the lattice and the Hermitian form for this 3 branch point cover. And if we can't do that, then the rest is impossible. So, so the condition of a type being simple is going to be important for this. And then we're also going to need to nail down the type for that 3 branch point cover. We're also going to need
can I ask another question?
Yeah.
I was just wondering if there's an easy example to show why simpleness is needed for that statement about the bijection.
I don't know. Some cases that are not simple are when the field is biquadratic. So if m is 8 or 12, you can run into trouble. Also, the cases of but we'll see that when m is 7, there's a type that's not simple. And so I don't have an example on the top of my head, but but I think you could maybe produce one by looking at how this last part, this part 4, that if you would take A and B to not be in the same ideal class, fractional ideals that are not in the same class, and then produce your lattice by looking at the image of those fractional ideals under phi, then you would get 2 complex tori, which would not be isomorphic. And I think that's how you'd produce an example like that.
Okay, thank you.
Yeah, so the data of the principal polarization is given by a Riemann form. And one thing that van Wamelen studied in a paper was how to explicitly nail down that principal polarization. And one way of doing it is to think about the extension L over L naught, and to find a generator for L over L naught. Let's call that generator Xi, so that the square of that generator is in L naught. So that's saying that we want it to be totally imaginary. And we also want the different of L over Q times AA bar to be generated by Xi inverse for some fractional ideal A of L. And if you have a Xi that looks like this, then you can define a Riemann form from L cross L to C. And the way to do it is by taking two entries in L and getting a tuple. So this is going to be a tuple, and phi of x will be a tuple in C to the n, where we take all the embeddings of x under the different embeddings in the CM type, and then using the trace. And so here's an explicit formula for this Riemann form. And the theorem that von Vommelen showed is that, let's say we look at Xi and look at its embedding into the complex numbers under all of the embeddings phi in capital Phi. Well, that has to be a totally imaginary number. And so we can see whether it's in the upper half plane or the lower half plane, so whether it has positive or negative imaginary part. And if the imaginary part is positive for all phi and phi, then this Riemann form defines a principal polarization of type L phi on C to the n mod phi of the fractional ideal A. And furthermore, if L phi is a simple CM type, then all principal polarizations of type L phi on this lattice, on this complex torus C to the n mod phi to the A, are given by such a Xi. And from this, von Vommelen produced an algorithm. It's not an algorithm that always ends successfully, but an algorithm to produce these principal polarizations. And what it boils down to is finding ideals A of L that give you information about the codifferent, and then understanding units in L. And then from this, he produces all the principal polarizations. So just a special case, which probably appears earlier in the literature as well, is that if phi is a CM type of L, and let's, instead of writing Xi, let's write beta. So this element beta in OL defines a principal polarization on this torus of CM type L phi if and only if beta generates the codifferent, beta is totally imaginary, and the imaginary part of phi of beta is positive for each phi and phi. And then we can also see we not only want to produce a principal polarization, we want to see if we can completely nail down that polarization. And so in order to do that, we need to understand, when do two polarizations give us isomorphic principally polarized abelian varieties? And from the previous slide, we can say that that comes about if there's a unit in UL, so that beta is U bar times beta prime. And furthermore, if the CM type is simple, then all principal polarizations of CM type OL phi will arise in this way. So, let me just give an example that, well, let me say one more thing about this. So we've seen now that really, just in order to understand just the 3 branch point case, to really nail it down, we're going to need to understand the class group, and we're going to need to understand units. And so here's just an example that these betas are not too complicated. So for the cyclotomic field Q zeta M, it's easy to compute a beta naught, which generates the codifferent and which is totally imaginary. For instance, this beta naught satisfies those properties. So you can see that since these two values, zeta m to the m plus 1 over 2 and zeta m to the m minus 1 over 2, since those are complex conjugates, this is definitely going to be on the imaginary axis. And then if you look at some notes by Keith Conrad about generating the codifferent, you can see it's generated by the derivative of the cyclotomic polynomial evaluated at zeta m. And so you can just check that this beta naught does that. So very explicitly, if m is 5, we take beta naught to be 5 divided by zeta 5 cubed minus zeta 5 squared. That will satisfy properties 1 and 2. But we still need to deal with condition 3, which is that we want the imaginary part of phi of beta to be positive for each phi and phi. And that's going to depend on which CM type we're working with. So the strategy is to look at all the signs of the embeddings of the imaginary parts of the embeddings of beta naught. And some of them might be positive and some of them might be negative. And what we want to do is adjust beta naught by something so that we have the right signs. But we can't mess up the property that beta generates the codifferent, so we need to multiply by a unit. And we also want to make sure that we stay on the imaginary axis, and so that unit needs to be totally real. And so we want to make this adjustment, and the question is this always possible? So for example, if m is 5 and if phi1 is sigma 1 and sigma 3, we could take the unit to be -1, and then this beta 1 will satisfy properties 1 through 3. And if phi2 is sigma 1 and sigma 2, we have to take a different totally real unit so that we satisfy property 3. So can we always find these units? And the answer is yes, as long as the real subfield L0 has independent signs, which basically means that you can just get every configuration of the signs for the totally real units. So if we fix an ordering of the real embeddings, we can say what it means to have independent signs, but as long as we have that property, we can generate a principal polarization. I think in the interest of time, I will just skip this slide, but this idea of having independent signs is closely connected with the narrow class group, which classifies the group of fractional ideals of L0 modulo principal ideals generated by a totally positive element. And it turns out that L0 has units of independent signs if and only if the narrow class group is isomorphic to the class group of L0. Okay, so to conclude this whole section, if L0 has units of independent signs, and if L phi is simple, then we can say there exists a principally polarized abelian variety of type OL phi, and it has at most one principal polarization up to isomorphism. And if in addition L has class number 1, then there's in fact a unique principally polarized CM abelian variety of type OL phi up to isomorphism. So those are some pretty stringent conditions. To say that the cyclotomic field has class number 1 only shows up for a finite list of odd m, some of which are primes, some of which are prime powers, and some of which are products of a small number of primes. But luckily, the narrow class number 1 condition doesn't add too many more restrictions, because if you look in a book of Connor and Hurlbrick, which I'd like to thank John Voigt for showing me, that because if you can just figure out how many finite primes ramify in L over L0, then you can determine the narrow class number. And the narrow class number is 1 for all the prime powers, and the narrow class number is 2 for the things that are not prime powers. All right, so we get to our main result then. So suppose we take the cyclotomic field Q zeta M, and suppose it has class number 1, and we take an arbitrary monodromy data, MNA. For now, let's let M to be an odd prime. And then first, what we show is that the Hurwitz space, Z gamma, has a distinguished point. Sometimes this point is called a totally degenerate point, but I think distinguished point sounds better. And it represents an admissible mu-m cover of a tree of projective lines. And And this curve is a curve of compact type. So that means that its dual graph has no cycles. So it's just a sort of a tree of curves of positive genus. And each of these curves has genus m-1/2 and admits a mu-m cover of P1 branched at 3 points. So the proof of this is not so hard if you're familiar with Hurwitz spaces and admissible covers. And then from that distinguished point, we're going to look at all the curves showing up in that distinguished point and look at their abelian varieties. And those are principally polarized abelian varieties of dimension m-1/2 with endomorphism ring OF. They have complex multiplication. So we'll take the CM type of that abelian variety, and we're going to assume that that CM type is simple. I'll say more about that condition in a minute. But that condition is automatically satisfied if m is 3, 5, 11, or 17, also for some of the prime powers. And then we'll let beta j be the value defined earlier for this CM type. And then the integral Shimura datum is going to be the vector space f to the r together with the standard OF lattice OF to the r. And the Hermitian form can be defined using the trace where we use this matrix capital B, which is a diagonal matrix with the entries beta 1 through beta r. Let me maybe go in a different, well, okay, so part 1 is somehow no big deal, involves clutching morphisms when m is prime. The idea is that if you have two mu-m covers, you can just smash them together by identifying the last ramified point of the one curve with the first ramification point of the other. And you get a singular curve whose Jacobian breaks up as the product of the Jacobians of the two original curves with the product polarization. And if it's admissible, so this is a little bit where the arithmetic of the monodromy datum starts to play a role, then it can be deformed to a mu-m cover of smooth curves. So we need the last entry of the first inertia type to be the negative of the first entry of the second inertia type mod m. And that's the condition under which you can deform this cover to, you can always deform this singular curve away from the boundary of the moduli space of curves into the interior of the moduli space of curves. But whether you can deform that while maintaining the mu-m action depends on this admissible condition. So for example, when m is 5 and n is 4 and a is 1, 2, 3, 4, here are the two covers that you would want to smash together. One has the inertia type 1, 2, 2, and the other has inertia type 3, 3, 4. And when you smash them together, it's admissible because 2 is the negative of 3 mod 5. And then those two ramification points disappear. And so on this first 3-point cover, the principal polarization is given by minus beta 1. And on the second 3-point cover, the principal polarization is given by positive beta 1. And so the integral Shimura datum for this Shimura variety has the Hermitian form with the matrix, the diagonal matrix, minus beta 1, beta 1. So this simple condition we see is crucial, and it's not always satisfied. So for example, when m is 7, if we take the sigma 1, sigma 2, sigma 4 to be our CM type, then that's not simple. It's induced from the quadratic field Q squared root minus 7. And you can in fact see this is the only problematic CM type when m is 7. And basically when m is congruent to 1 mod 3, you will consistently have this problem. But there's some cases where life is automatically simple, maybe not quite as many as we would like to have. But if m is 4, or if m is a Fermat prime or twice a Fermat prime, then you're automatically simple because your field has no proper non-trivial CM fields. So you just get this condition for free. So for example, that works for M being 4, 3, 5, 17, 6, and 10. With a little more work, you can show that life is automatically simple for the CM types if M is 9 or if M is 3 mod 8, because in that case, there's only one proper non-trivial CM subfield coming from the subgroup of Z mod M star given by the squares. And the CM type will be simple as long as it contains an embedding for both a square and a non-square. And under some quadratic reciprocity conditions, you can show that that's true. So from this, for example, we can handle all of the cases, all of the Hurwitz families when M is 3. And in that case, it's not so complicated to write down the signature, because for the Z mod 3 action, we only have 2 eigenspaces. So we only have 2 values, F1 and F2. And the inertia type, the number of 1s and the number of 2s in the inertia type is determined by F1 and F2. And so, and the only options are beta 1 being minus the square root of minus 3 and beta 2 being plus the square root of minus 3. And so for the Hurwitz families, when M equals 3, we can do all of them. Here are 2 examples when M equals 5. These examples are special. They're in the Monin table for M11 and M16. And these are the Shimura, integral Shimura data for those families. And I guess I still have some time, so maybe I shouldn't have blitzed through those previous slides, but I just want to tell you about some possible generalizations. In particular, it would be nice to be able to handle more general values of M. And in those cases, so far we can only find the integral Shimura data under some conditions on the inertia type. So lots of things can go wrong if M is not an odd prime. One complication is that the Hurwitz family might not have any distinguished points of compact type. Somehow what that means is that the Shimura variety itself is compact in the moduli space of abelian varieties. It doesn't hit the boundary of the only degenerations happen for things that are not of compact type. Those are, of course, going to correspond to curves that have that self-intersect. So their dual graph has loops in them, and that we really sort of don't have a strategy for dealing with those cases from the perspective I talked about today. And that happens quite frequently. So for example, the 12th Monin family, where M is 6 and N is 4 and A is 1, 1, 1, 3, that has no degenerations of compact type. You can kind of see that because if you sort of smash these 2 branch points together, the 1 and the 1, you have to smash a branch point together with another one, a 1 with a 1. And then the last, and that can only come from the inertia type 1, 1, 4 together with 2, 1, 3. And that situation, you have to identify the 2 curves at 2 points rather than at 1 point. And so that's why you get a cycle in the dual graph. So if M is not an odd prime, another thing that can happen is that we get some distinguished points of compact type involve induced covers, meaning that the cover will be disconnected over one component of the tree. For example, that happens with the Monin 18 family. That somehow is not too big a deal, but it just involves more bookkeeping, dealing with the algebras, not the fields, and doing some other things. And then some distinguished points involve non-simple CM types. So for example, the monon family M17, when M is 7, N is 4, and A is 2, 4, 4, 4. Sorry, I just need to plug in my computer. That is a case where any degeneration is going to be non-simple because it will involve one 3-point cover with A being 2, 4, 1, and that one was not simple. So we have some strategies we're in the midst of to deal with those other cases. So for example, this A references this item 1. No, excuse me. This A references item 2. This was a case where M was 2 times an odd prime, and that involves the induced covers, and we have some strategies for that case. For example, we found the integral Shimura datum for M18. When M is a prime power, we also are working with induced covers. But another strategy that works very well for these 4 branch point covers is if the family has a different distinguished point representing a curve with extra automorphisms. And so, for example, we found the Shimura datum for M17, which was one of the ones that we couldn't do before. And so that strategy puts constraints on which inertia types we can handle. And it also uses a lot more algebraic number theory, but it does circumvent the problem of having non-simple CM types. Okay, so let me just say in conclusion, so this talk, we looked at Hurwitz families given by different monodromy data, and each of them was attached to a component of a Shimura variety, and we used the Hurwitz family to figure out the Shimura datum for that component of the Shimura variety. And to do that, we used the 3 branch point covers, and we figured out which conditions on the class group of the cyclotomic field and which conditions on having simple type would allow us to nail down the abelian variety and the principal polarization precisely. And that's all. Thank you.
Thank you very much, Rachel, for a very, very nice talk. I enjoyed the examples particularly.